Hi, today we'll talk about in a conference in Suzhou, China, II organized by IIVEA. So my topic is RISC-V based AI MCU used in biomedical devices in space application and in automobiles. So this presentation is being organized and presented by IIVEA and with a full support of TEMS to innovation, TEMMS, which means technology, engineering, medical, mathematics, and science. So we don't use STEM. Why don't we use STEM? Because it doesn't have medical inside. So we start with my biography. I'm Professor Dr. Mehdi David. I was the ex-professor in Honan University of Arts and Science. So I was teaching some courses there. I'm a senior consultant for Total Artificial Heart. I'm a senior consultant for RFIC, MMIC, ASIC, MCU, and nanotechnology, especially for radio astronomy hardware design. I'm a CTO and a co-founder for Upselling Robotics, which is for biomedical devices, especially total artificial heart, VAD, um, digital stethoscopes, ECG, AI-based, and this company is being founded since 2006 till now. It's been 19 years I'm working in this company, and it was started inside the hospital. The second company, a CTO, I'm a co-founder for Space Radio Astronomy, for radio space hardware design at terahertz frequency, design in a clean room nanotechnology. I founded this company in 2017. I worked for some months, some time in NASA for radio astronomy projects for Alma, Chile. Moreover, I'm a CEO and co-founder for Upstream Heart Transplant Hospital, which is which is founded in 2024. The main objective is to implant total artificial heart designed by Offspring Robotics and VAD. Moreover, I'm a patron and founder for the Journal of Medical Electronics and Mechanical Circuit Support. I'm also a patron and, and co-founder for International Society of Medical Electronics and Mechanical Circuit Support. Here we go. So this will be the content. Uh, it's like we talk about three companies: Upstream Robotics, Space Radio Astronomy, Upstream Heart Transplant Hospital. And we talk about the core team, introduction, RISC-V CPU, RISC-V based CPU diversity, upselling robotics, RISC-V based AI MCU, space radio astronomy, RISC-V based AI MCU, upselling heart transplant. We talk about the RISC-V based AI MCUs or artificial heart transplant, automotive industry based RISC-V based MCUs, and last and not least, the applications for RISC-V based AI MCU, and eventually we reach to a conclusion. Okay, this is my core team. I'm the on the top because I'm the CTO, and not only CTO, I'm the chairman because I this is my idea of these three companies. So that's why I'm a chairman. And down you can see many doctors. Some are from Pakistan, and many are from China. I'm definitely collaborate with Chinese professor for our project. And I'm the head of MCU. Main objective to make a AI best MCU for our devices. Also mechanical structures for total artificial heart uh, and for radio astronomy, etc. So this is the same thing, but in Chinese. Because I have a conference in China, so I decided to keep both things inside so that people should understand. I give it 10 seconds uh, stop so that people understand what is written here. Okay, now it's time for the introduction. So what are the trend in hardware design? We have so many processors in the market perpetually, where you have to pay the money, like ARM, Intel, AMD, NVIDIA, where you have to pay huge money for the perpetual, for the IP. The big key problem with these things is like the performance characterization requirement is a lot of effort, and we have to get it right. So eventually, the best thing we can go for the open source. And the best thing right now in the market, which we can see is the best for the open source, is the RISC-V based processors, and which makes our time consumption lesser, less effort, and get easily we get our target which we want. So here we go. This is the Chinese slide, so that people just go around what I mean. I give 10 seconds or 5 seconds delay. Here we go. Golden age of silicon diversity. This is we call this era. We have a silicon heterogeneity. We have so many silicon heterogeneity. We have architecture variety. We have so many architecture right in the market, which we think which some have power consumption less, some have a high power, but the efficiency is very good. So we can choose anything right now in the market. We have so many. We have multi-vendor silicon landscape. We have multi-vendors. So many vendors. We have gallium nitride, gallium arsenide. We have 3.5, we have 3.4, silicon carbide, silicon base. We can go for any landscape for our project, for our hardware design. We have so many design compatibility. We have so many designs, and we can choose anyone. Some may be a size is smaller, some might have bigger size, but it has some facility which can give you more. And on the right on the picture side, you can see AI personalization. A woman, a Chinese woman, with a robot. She's guiding her what is her plans, and she's writing everything for her. So this is what we call golden age. And on the right side, you can see ubiquitous AI compute. You can see an aeroplane flying with some with have a AI interconnect with each other. The cars, the robot is moving, the post robots, and everything interconnect with each other and with AI and understand these things. So that we call golden age of silicon diversity. Here we go. So we can see on here on the left side on top, automotive, we can see we have so many companies right now in the market, like Infineon, Carters, MIPS, NDS, High Tech. They advocate for the automotive in technical group and SIGs. And we can maintain gap analysis, we can interface with the industrial initiative, we can go investigate AI for automotive applications, development of the RISC-V auto technology, develop ecosystem support uh, for in this automotive with RISC-V base. Also for the RISC-V, we can go for the space application, understand space requirement, advocate for space in technical group and SIGs, maintain a gap analysis, investigate AI and HIPS, leading edge security capability, and there are many companies like for the space applications, S5, NASA is also using S5 microchip and everything. And on the right side, we can see the biomedical devices, like we have so many biomedical ECGs, X-rays, MRI, artificial heart. They are using like NDRs, NVIDIA, ahead computing, a kind of this thing with the artificial intelligence, with AI, ML, special interest group, explore new data format and algorithm versus vector and matrix extension. Okay, and this is the Chinese version of this slide. So it will make it easier for the Chinese to understand what I was saying. I'll give it some little time so that they can see. Okay, so RISC-V origin story, but it was pronounced as a RISC-V. So it started as a research project in 2010 at UC Berkeley. Commercially, ISA were too complex, the companies, and presented IP legal issues like ARM, uh, SIVA, etc. So RISC-V defined as ISA specification. So there are two main specifications, user level and privilege level specification. So user level is currently frozen at version 2, released in May 2014. The privilege level architecture is currently at version 1.10. So RISC-V is available freely under a permissive license. So the thing is that RISC-V is not a company, it is a CPU implementation. And on the right side, you can see the professor from Korea. And these people were the one who founded this RISC-V. This is the Chinese version for this slide so that you can see and understand what I was saying. Okay, the thing about the open source hardware is it can be scalable, it can be extensible, more efficient as compared to closed, and more stable. We can do many things with the open source hardware. We can change many aspects as compared to if we buy perpetual like ARM, SIVA, where we have some limitations. But in open source, we don't have any limitations. We can design our own and decide what we have to do, which make it more scalable, extensible, efficient, and stable for our project. Okay, now I'll talk about the RISC-V CPU diversity. Okay, in the market right now, the RISC-V market research by SHD Group, they say the revenue system on chip is 2.8x in 2023. 23, it was 2.8 times higher than before, and it will reach to 15x from 2023 to 2030, which is a huge step for the revenue in SoC. So we can see on the left side, the mobiles, they're using RISC-V, the Bluetooth, the Wi-Fi, MediaTek, they use RISC-V, the storage and the performance bandwidth, Python is using this thing, the 5G network, and MPU, MCUs, like Genesis, they're using RISC-V, this thing. And on the right side, you can see the accelerator bandwidth extension using the RISC-V technology, and we can use also in display and touch auto MCUs and auto DVR camps. In almost every field we can find this MCU, the RISC-V based. Okay, the NDS lineup, core lineup, they used to sell their own processors on RISC-V based. So you can choose categories. They are categorized. They're categorized by the power efficient, the balance, extended fuse. What do you want? So it depends on you. If you need a 40 series with power efficient, you can go for N45. If you go for balance, then D45. The same for the 25 series, which is the 40 was 8 stage, and go for 25 series, which is 5 stage, fast and compact, and the 8 stage was super scalar. So where you can go for the balance, you can use this one, and also divided into compute, Linux, and FUSA. This is how we characterize while choosing which processor we should use for our project. This is the Chinese version. Okay, now I'll talk about the company, Opsiling Robotics, RISC-V based MCUs. Okay, this company like Opsiling Robotics using the RISC-V based MCUs for the total artificial art. You can see on the left side is a heart designed in 3D printers, and you can see right inside there you can see a chip. So this chip is like is a RISC-V processor with using NDS technology CPU, NDS Air NDLA 1350, which is very good for AI for ML. And so we use for in offsetting robotics we use this processor, and on the right side you can see the emulation board to test the chip. And on down you can see the simulations to make the best structure for this artificial heart to be designed for the human. So this is more like we can use biomedical devices RISC-V based MCUs as well. So this is like on the left side you can see more like these chip inside. What we have a CPU RISC-V, we have a NDRs, we have 512 KB L2 cache, DMA, and then this is a RISC for total artificial heart with a peripheral, with on-chip memory, and etc. Moreover, you can see here, this is the RISC-V based AMC total artificial heart, which we name UR-EMDA. UR means Opsling Robotics. EMDA is the name of the chip. And you can see everything, the combined EF with RISC-V MCU subsystem 1 plus 4 core pill architecture, low power control performance processor, autonomous IO further subsystem, further SoC detail. And then you can see on the left side the chip and the chip number. This is the Chinese slide, so the people can understand what is written. Okay, the space radio astronomy RISC-V based AI MCUs. So the state space. So we also use MCUs for the RISC-V based. Why we use the processors? Because when we have a high frequency signal from the space, we make it to we down convert to the IF signal, and after IF we have to do some signal processing. So eventually we use RISC-V based MCUs, AMCUs for space application astronomy, and then we can do some calculation to understand the signal level, what it means. So we use RISC-V processor, same with like for the artificial heart, NDS technology CPU with ANDL because it has a AI/ML inside, machine learning technology. And on the left side, you can see for hardware, a signal coming from to the antenna with SIS mixer with down convert to the IF signal 1.5 gigahertz with the IF signal processing. Then it go to the processor MCU for further signal processing. So this is the space radio astronomy. On the left side is the hardware inside. So what we have is almost same like Upstream Robotics, a total artificial heart and the core. It has the RISC-V with the 512 KB DMA, and we can use for different things, and also wireless baseband and 2.4 gigahertz RF. So this is like now we'll talk about the Upstream Heart Transplant Hospital, the third company. It's a RISC-V based AMC total artificial heart implant. So this is like on the left side. First you will see a total artificial inside. Then we do some simulations, and it reached to make a mechanical hardware of artificial heart, and we put the chip. Afterwards, we go for implant inside the human body when it has a heart failure. So this is for our company, Upstream Heart Transplant. What it'll do, it will make a total artificial heart, so make a mechanical structure, make a chip, everything. Afterwards, after some test and everything, FDA approved, we go for the we go for human test, third trial. So we use RISC-V. Okay, now I'll talk about the automotive industry in RISC-V based AI MCUs. So automotive as a sandbox. For decades, automotive has been seen as a separate ecosystem. Long development cycles, unique requirements, including safety, complex tire system, extremely resist to change. Closest analog is in industry. So we can see that in automotive and semiconductor, we have ISO 26262. Safety compliance temperature should be minus 40 to 125 and should be 10 to 15 years product life cycle. So industrial semiconductor focus on drug reliability, diverse application, shorter development cycle, which we can achieve from the RISC-V. This is the Chinese version for this slide, so that people should understand what I said. Okay, so the software development vehicle revolution, which is we call SDV, you can see from here the explosive market growth. We have a so huge market growth. OMD expect OEM software and digital investment to triple by 2035. So on the right side, you can see the sale of software-defined vehicle based on centralized domain, E by E, architecture by the type of OEM. You can see from 2019, the the distributor was around point 0.2 million, and the incubator is zero. But when we reach to 2024, 2025, we can see a rise, start rising like around the distributor is reached to from 0.2 to 1.3 million, and then incubant reach 2.2 million, 2.5 million. Eventually, we can see in 2036, it can reach a huge to the distributor can reach up to around 3.8 million, and incubatant can reach up to 2 million. So we can see from here the industry transformation. 75% of industry leaders expect software-defined experience to be core to automotive brand value by 2035. Shift from traditional hardware-dependent model to flexible software platform. Growing emphasis on predictive maintenance and AI-powered diagnosis. And now you can see from here, high, ARM, which is a perpetual paid software, paid uh, hardware IP, and which have high fragmented, difficult to scale. On the right side, you can see the RISC-V, clean, simplify, centralized software first approach. So this we can see from here, instead of using ARM or other CIVA or other IP, we should go for this free IP RISC-V, which give us clean, simplify, centralized software first approach. This is the Chinese version, so people can understand. Okay, the software-defined vehicle revolution in practical terms, we can see here. The RISC-V is strongest in the most significant area of both intelligent automotive and industry. We can see a safe, secure, scalable, development time independent, and right size intelligent. And we can see from between 30 to 150 ECUs in distributed architecture. The modern consolidate E by E architecture, such as centralized domain and zone architecture, offers several key benefits, like integration of high performance computing within consolidation ECU, decoupling of hardware and software for greater flexibility and scalability, use of advanced technologies such as Ethernet for fast communication between ECU and vehicle sensors, seamless connection of vehicle system and sensor to the cloud, enabling frequent and reliable over-the-air OTA updates, sophisticated interconnected vehicle feature that use cross-domain and cloud data. Also, we can see reduction in the number of physical components such as cable hardness, which decrease vehicle weight, a critical factor for improving the range of electrical vehicles. Moreover, simplification of the physical architecture result easier manufacture process, enhance update capability, and potentially lower overall cost. This is the revolution for the SDVs for the RISC-V. This is the Chinese version. Here we go. So we can see the opportunity in regional development cycle. China predicted to be the locus of software-defined vehicle RISC-V industry automation. We can see from here on the left side, the forecast top 10 leading OEM by software-defined vehicle sales market share in 2030. Like BYD is 35, 31%. Tesla is 24, which is 7% lower than the BYD. And then we can see the other Chinese manufacturers like BMW, Mercedes 5% around. And then in the middle, we can see the intelligent industrial automation unit by region by 2020 to 2030. We can see the Americans in 2020, it is around 3, which can reach to 3 to around 7.9. In 2030, the Americans from 4, which was 3, can reach up to around 12, approximate 12, which is quite high. And on the other hand, the European Union, the Asians, we can see they also scale up a lot. And then on the right side, the figure, you can see RISC-V processors in industry application by region 2020-23, the American, the European, the Asians. You can see 2022, which is around the maximum of each is around 6, which can up to reach to 25, which is quite high as compared to 6 from 2022 2030 within 10 years. This is the Chinese version. Okay, the RISC-V based AI MCU, the applications. Okay, here we go. So the RISC-V based AI MCU, the ND, we was talking about the NDS NDL 1350, which we use in biomedical and space radio astronomy. Why? It has a high performance, efficient deep learning accelerator for edge and endpoint interface. It configurable MAC for 32 to 4096 integer 8. Can have a maximum performance 8 tops at 1 gigahertz. Configurable local memory which can do 16 KB to 4 MB. Multi-dimension DMA for 64-bit AXI bus interface, NN type CNN interface. We can have NN model, image and video LXNet, VGG, mobile net. We have tiny YOLO and SSD mobile net inception. We can have speech, voice, and audio LSTM, RN, GRU. We can have operator, convolution, depth-wise convolution, point-wise convolution, transpose convolution, dilated convolution, element-wise, full connection activity, and we have upsample, concatenation, batch normalization, channel paddling. We can have operator fusion and NHWC data format while using the RISC-V based AI MCU using NDS34 CPU. This is the Chinese version. Okay, now I'll talk about the application RISC-V based AI MCU. We can see on the right side the one we use NDL 1350, the block diagram. It can be a IoT device, AI IoT device, tiny ML on edge endpoint, biomedical device design. It can be used for the biomedical device design. It can be used for the radio astronomy space, automotive industry, smart sensors, sensor hub, wearable, smart home appliances, and robotics. We can use in many applications. And on the right side, you can see the block diagram for this CPU, which have a DMA, general matrix, convolution accumulator, element-wise data processing, pooling feature. Conclusion. Okay, so we conclude that RISC-V AMC for all computing devices. RISC-V is emerging as a major application platform. RISC-V helped in lowering SoC design entire entry barrier, extremely low power consumption, high computing efficient, AI personalization. You can see AI computing, golden age of silicon diversity, high performance CPU roadmap. So these are the companies' dependency on RISC-V. You can see this is a huge big companies. You can see Qualcomm, the Google, Nvidia, IBM, the very big Samsung, MediaTek, Alibaba, NXP, Infineon, TSMC, Magic Graphics, S5, Bitman, Dolphin. We can see a lot of companies, they are dependent right now on the RISC-V. And the universities like ETC are a very good Cadence, a very good silicon software, Synopsys, they are all connected with the RISC-V. This like free, open, extensible ISA for all computing devices. Okay, so this is our conclusion. Upstream robotic space radio astronomy, upstream heart transplant hospital. It has partnered with the Chip Motion, IC Cafe, upstream heart transplant, space astronomy, ATM, USDC, upstream robotics, and with thanks to TEM's innovation for this presentation, which is means technology, engineering, medical, mathematics, and science, who help us to get connected with this Chinese Suzhou conference on IIVEC. So if you have any questions, you can ask me. Thank you.